Hey there, in this video I want to look at a problem we can run into when we do Gaussian elimination. So in Gaussian elimination we have two things we can do. We can divide and we can subtract. Subtraction is very safe. Division on the other hand, well, what happens if we try to divide by 0? We're going to end up crashing our program. So we want to make sure, we want to guarantee that we don't ever try to divide by 0. And I'm not even talking about equations that don't have solutions. If the equations don't have solutions, it's hopeless anyway. Now, if we're doing physics, we're always going to be doing real-world systems, and real-world systems have solutions, so we won't actually run into that problem in physics. But what we can run into is the order of the rows in the matrix could be such that at some step you just need to divide by 0 the way it's laid out. And if only the equations were written in a different order, we would have been fine. And the solution to that is to just make sure we write the equations in the correct order to begin with. This is called partial pivoting. In linear algebra, pivoting is when you switch rows or columns in a matrix. Partial here means we're only going to change one of those. Specifically, we're only going to change the rows in our matrix. And this is all just because division by 0 is bad. So let's look at an example. Let's say that our set of equations ends up giving this the matrix equation 0, 1, 2, 1, 1, 1, 2, 2, 1. XYZ is equal to 1, 0, 2. This has a solution, but the way it's written, we're going to immediately run into trouble trying to do our Gaussian elimination, because step 1 would be divide everything by 0. And, of course we can't do that. So the solution to this is, before we do a division step, always before a division step, check. Look in the current column you're working at and figure out which row is the largest, and then swap that row with the current row. So in this case, the rows on our matrix are 0, 1, 2, 1, 1, 1, and 2, 2, 1. And the biggest of those is 2, 2, 1. What I want to do is I want to take 2, 2, 1 and then swap it up here in place of the first row. Now, of course, if I'm changing something on the left-hand side of my equation, I also have to change it on the right-hand side. So I want to make sure that I swap those, the 2 and the 1. And what we'll end up with is 2, 2, 1, 1, 1, 1, 0, 1, 2, XYZ equals 2, 0, 1. And so now we continue doing our Gaussian elimination. We're going to subtract multiples of the first row from the second and third row. So after we do that step, we're going to end up here with like say I want to get a 0 here in the second row. I need to subtract 1/2 times the first row. So I've got my simplified first row is going to be 1, 1, 1/2. And then I'm going to subtract that, so I'm going to get 0, 0, 1/2. And then my third row would be 0, 1, 2. So that's just your next few steps in Gaussian elimination gets you there. And then on the right hand side, we're going to have a 1, negative 1, 1. But look, we've got a problem again, because the next thing we're supposed to do is divide by 0. Okay, we can't do that. So we partial pivot again. We're going to take the third row and swap it with the current second row. Same thing over here on the right. And then we can continue doing our Gaussian elimination. We will end up then with x equals negative 3, y equals 5, z equals negative 2. So this does have a solution. Now, when you write a program that does the partial pivoting, you can actually combine these swaps, because it turns out pivoting in linear algebra can be handled as a matrix multiplication. Specifically, a matrix multiplication from the left will let us handle permuting the different rows. And so that's called a permutation matrix P. So in this case, we could have ended up with the very same result if we first multiplied our matrix A by a permutation matrix 0, 0, 1, 1, 0, 0, 0, 1, 0. And what we would end up getting after swapping it around is we would have A in what you could call the correct order, where we wouldn't have run into any trouble from the get-go. So this first term is a permutation matrix P. A permutation matrix always has 0s and 1s in it. And you're going to have exactly one row in each row and 1, 1 in each row in each column. Multiply that from the left to matrix A, and then on the right here we'd have P times A. So the only sort of tricky part, I guess, would be picking out, which is your biggest row as you sweep through the matrix. So, looking at the matrix here, we'd see, like, if we order these by size, at the very bottom, that would be the largest of the rows, so like 2, 2, 1. And now we're going to ignore the first column and then look at what's left, 1, 2, or 1, 1. Okay, it looks like 1, 2 is the biggest, and then we ignore the next column. What's left? There's only one thing left. It has to be 3. And so then if we come back over here to our permutation matrix on the left, the location of those ones when you do a matrix multiplication are to pick out each of the rows. So like we saw that the bottom row, row 3, is going to be the biggest for the first step, and you notice this 1 here is going to give us row 3 up here at the top, and then so on. So all you have to do is sweep through your matrix with a little bit of code, and then you can from that create a permutation matrix P, matrix multiply it in your code, and then you just go through Gaussian elimination from there. And that's what the main solver in Python does.